Hello everybody and welcome to a new video on this channel after a long time. So, today I will talk about how to perform system identification, part 1. So, what does it mean? System identification means we have an unknown system and we want to know the coefficients that describe the system. Think about a linear system, FIR-Filter for example. It's a vector containing some values describing the system. It's the impulse response. And so assume we know the input signal to the system and we know the output signal to the system of the system. And from these two signals we want to estimate the system coefficients. So the unknown vector. Probably the output signal that we measure will be corrupted with noise because of our measurement errors or something else. So, but assume we know the output signal of the system containing some noise, measurement noise, and the input signal. And from these two signals we want to estimate the system response. And there are a lot of algorithms that can do this. The simplest idea would be, let's take the FFT of the output signal, let's take the FFT of the input signal and divide both, and then take the inverse Fourier transform and we have our impulse response of the unknown system. But this is the let's say the most erroneous estimator that we could use for that. Estimator that is a bit more fancy or a bit more efficient with a better accuracy is the least mean square algorithm. So the least mean square algorithm, you will find it everywhere. It's a learning algorithm, also used for machine learning, system identification and a lot of stuff. And it's only one algorithm inside the family of adaptive filters. You also have recursive, least mean square and a bunch of other algorithms. But let's start with the basic least mean square estimator that we can use for this purpose to estimate the unknown coefficients describing our system. So let's directly head over to our Octave workspace, and as usual, even after that long time, we start with the three well-known lines: clear all, clearing all workspace variables, close all, close all maybe open window, and CLC, clearing our command window. So first let's define a system. Let's call our system H. So let's say it's 1, 2, 0.5. So these three values are the impulse response of our system. 1, 2, 0.5. And this system we want to estimate. And now, as I described, we need an input signal that we can feed into the system, and we can measure the output signal. And from input and output signal we want to estimate H. So let's define an input signal. Let's say we take noise, random noise, with n values. So let's define n. Let's say n are 1000 samples. So we generate a signal X, a random signal X containing 1000 samples of a Gaussian normal distribution. And now let's feed this signal into the system. And what does it mean? Passing a signal into a linear system means that we convolve the impulse response H with our signal X. So we could use the conv command from Octave, or we could use the filter command. So let's say Y, so the output will be, well, let's rename it to input and output. So we use the filter command. To the filter command we pass our filter coefficients H, then a 1, because the filter command can also be used for IIR, infinite impulse response filters. So this is a filter that has a nominator and a denominator, and we all only have the vector H, so we only pass H and then a 1 and then our signal input. let's just fire it up to see how the output signal looks like. I will plot the output. So let's have a look at it. So okay, here we have it. So here we have the output signal of our system. So we fed our random vector x into the system in our 3 value system, and this is the output signal. And now let's add some noise to it, because in the real world we are not able to measure the output signal exactly. It will be corrupted with some measurement noise, some uncertainty. And we can model this uncertainty by just adding some small amount of noise to our output signal. Let's say the noise has the amplitude 0.5 and the same dimension as our input signal, so n samples. So again, let's fire it up. Let's have a look at the output signal. So here it is. So here we have our noise corrupted output signal. For sure it looks different to the first approach, because each time we fire up the script, a new random vector will be generated. But as you can see, our noise with the amplitude of 0.5 will not influence our output signal that much, but it's nice to have or to simulate the noise, because as I mentioned, in the real world scenario we will have measurement noise. So okay, input and output, these are our 2 signals that we know, that we can measure. And from these 2 signals we now want to measure h. So at the moment we don't know h, so we want to estimate it, and we call it hest for h estimate. And we assume that it's a vector containing 3 values, so 3.1 zeros. This will be the starting point of our estimation. We fill everything with 0. And now what does the least mean square algorithm do? So the least mean square algorithm takes a buffer containing as many input samples as our unknown vector needs, so 3. So we have 3 values from h that we want to estimate. So in each iteration of our LMS algorithm we take 3 input samples from our vector input, and then we perform the LMS algorithm. We'll see it later. And then we have, for each iteration we get an estimate of h estimate. And for performing several iterations from each iteration, we will get closer to our values of h. But we will see it in a moment. So we define a for loop where we iterate over the input vector input, and each iteration we take 3 samples. So let's say it's sample idx as our loop variable, and the sample idx variable will start at 3 and will go up to n, because we have 1000 samples. So, and we have n. Okay, so now we define this buffer. So in each iteration we take 3 values of our input vector. In the next iteration we shift the buffer by 1 sample to the left, and again to the left in the next iteration, and so on. Each time we take 3 samples. So let's call this vector, this buffer, well, let's call it buffer. So, and buffer takes from input 3 samples. So the actual window starts at IDX, sample IDX -1 until sample IDX -3 plus 1. Why is it that complicated? It's a sliding window. Let's fire it up and you will see that now we will slide through our input signal vector, and in each iteration we shift our buffer one to the left. So if we, for example, have a look at the last three values here of buffer, because it's now at the end of our input vector, and let's have a look at the last three values of our input vector. We see these are the last three samples of our input vector. So okay, so for each iteration we now have three samples from our input vector. And what are we doing now? So we have to calculate with this actual buffer and our actual estimate of our system, HS, we have to calculate a temporary output signal. So let's call it output temp. And output temp is nothing else at HS times our buffer. We could also use the convolution command, and I used here the transpose sign. This is because output temp to at the moment in each iteration is a single value, and HS is a vector containing three rows and one column, and buffer is containing also three columns and one row, and so I have to transpose it that we get only a single value. So this is 1 times 3 times 3 times 1 result in a scalar value. So let's fire it up. Okay, so we have no error with our matrix dimensions. And so now we have a temporary output estimate according to our temporary system estimation, HS. At the moment it's 0, but from in each iteration HS will change. And the longer we iterate, the closer we will get to our real values from H. So, but now we have a temporary output signal, and we know the real output signal corrupted with noise, and now let's define an error. So the error of our estimation to the real value. So let's call it error for ERR. And error is nothing else than our output temp. Sorry, our output minus output temp. But output is a vector, output temp is only a scalar value, so we have to compare our temporary output with our real output signal at our sample IDX. So again, let's fire it up just to check if we made some errors with the matrix dimensions or with the loop variables. So no errors. So now we have an error depending or according to our actual or temporary output signal to our temporary system estimate. And now let's update our system estimated coefficients. So HS for the next run will be our HS at the moment plus a so-called learning factor. Often it's called mu. And this mu, you maybe know it if you have a look into the math for steepest descent algorithms, meaning, okay, there's some optimum value, and in each iteration we want to get closer to that optimum value. And the step size, so meaning the jump from one to the next step, is defined by this learning on mu value. And so it's a value between 0 and 1, so meaning the closer it is to 1, the faster we will come to our optimum value, but we will then swing around our optimum value. So the closer the value is to 0, small learning factors we will take longer to get to our optimum value, but the swing around the optimum value will not be that great. So if you would implement this in a running system, you would implement an adaptation of this learning factor. So you would start with a bigger value, and after several iterations, if the error is getting smaller, you would reduce the learning factor to get more precise. So, but for our simple example, let's say we take a value of 0.2. Don't forget, learning factor between 1 and 0. And then we have to multiply. This is now the math of the least mean square algorithm. I will link in the description of this video the Wikipedia entry describing this algorithm, so if you are interested how to derive this formula, but for the moment you have to trust me. So we take our actual system estimate plus our learning factor times our temporary output temporary input buffer, it's only called buffer, times our temporary error, ERR. So let's fire it up just to check if we made any index errors or matrix errors. So it's running. So now let's have a look of the convergence of this algorithm. Don't forget, we start with H estimate filled with zeros, and in each iteration we now take from our input signal that we know that we can measure without any noise. Also in a real world scenario, input would be corrupted with noise. We take 3 input samples, and in each iteration we shift our window to the left and take the next 3 input samples and so on. We calculate a temporary output value according to our actual input buffer and our system estimation. And we calculate the error. For each iteration, the error of the measured output signal output and our temporary output. And using these values, we make an adaptation. We estimate for the next iteration, we estimate the filter coefficients or the system coefficients according to this formula, the least mean square solver. So let's fire it up. And here it is. So what can we see? Just by having a look at the output of the command window, we see that in each iteration our system coefficients slightly change. They change, and at the end, after 1000 iterations, or 1000 minus 3 iterations, we reach a value of 1.2, 2.04 and 0.55. And now let's plot our estimated system values against our real system values. So let's configure. And here we use the stem command. Stem is a nice plot function for plotting discrete values. So we plot H, so our real signal, or our real system impulse response. And so hold on, that we can plot both in the same graph, and we plot H estimate, our estimated system coefficients, and we turn a grid on because the plot looks nicer. Grid minor, then the lines of the grid are smaller, and we give it a X label. X label is it's the impulse response, so we call it impulse response coefficient. Impulse response coefficient, and a Y label. We give it the name amplitude. So, and now let's fire it up and have a look at the plot. Keep in mind, because we generate here random signals, each time you run the script you will get different values, because the random number generator will generate new random numbers. But you can avoid this by forcing the random number generator to start at the same numbers by using the RNG default command. So let's fire it up. Okay. We forgot something important. We add a legend because we want to know which plot is what. So the first thing that we plotted is H, our real system. Let's call it real system. And the second plot is our estimated system. system. So let's fire it up. And let's add a semicolon here to avoid the output in the command line. And now let's have a look at the plot. I can already see it and it looks fine. So here it is. So what do we have here? We have here our real system coefficients in blue and our estimated system coefficients in purple, and as we can see, it's close. So this easy algorithm is able to estimate the unknown system in a very easy mathematical way. If we have a closer look, we see we have only a small error here. And for sure, we can increase the accuracy by, for example, taking more samples into account. At the moment, we take 1,000 samples for our estimation, and we could increase it to 10,000, for example. Let's increase it to 10,000 and plot it again. So then we get a bit closer. We still have an error here, but let's head over to that you also can see the output. So we now got a bit closer here in our first coefficient and in our third coefficient. We also got better here. We have here a deviation of, I don't know, difference of 0.4, something like that. So adding more samples, we will again get better, and we could also adapt our learning rate. And as I already mentioned, in a real world scenario, you would probably start with the higher learning rate or higher factor mu, for example 0.9, 0.7, and then from time to time you would adapt this value. So the closer you get to your optimum, you would reduce this learning factor to avoid the swing around the optimum value. So this is the least mean square algorithm that you can use for learning purposes, or as we did it here, for system identification, unknown system identification. System identification is important in several fields of signal processing and engineering, or electrical engineering. And so from time to time I will present here different algorithms performing system identification. And this was the beginning. So I hope you guys enjoyed the video, and if you like that content, give me a like. And so we will see us the next time. Bye bye.